Reasoning with the resolution principle is analogous to reasoning with other rules of inference. We start with premises, we apply the resolution principle to those premises, and apply the rule to the results of those applications, and so forth until we get to our desired conclusion. A resolution derivation of a conclusion from a set of premises is a finite sequence of clauses terminating in the conclusion in which each clause is either a premise or the result of applying the resolution principle to earlier elements of the sequence. Note that our definition of resolution derivation here is analogous to our definition of linear proof. However, in this case, we did not use the word proof because we're reserving that word for a slightly different concept, which we will see shortly. In many cases, it's possible to find resolution derivations of conclusions from premises. Suppose, for example, we are given the clauses not P or R, and not Q or R, and P or Q. Then we can derive the conclusion R as shown here. After writing down our premises, we resolve the clause on line 1 with the clause on line 3 to produce the clause on line 4. Then we resolve this clause with the clause on line 2 to derive the result on line 5. It's noteworthy that the resolution principle is not generatively complete. That is, it's not possible to find resolution derivations for all clauses that are logically entailed by a set of premise clauses. For example, given the clause P and the clause Q, there's no resolution derivation of the clause P or Q, despite the fact that it's logically entailed by the premises in this case. As another example, consider that valid clauses, such as P or not P, are always true, and so they are logically entailed by any set of premises, including the empty set of premises. However, propositional resolution requires some premises to have any effect. Given an empty set of premises, we would not be able to derive any conclusions, including these valid clauses. On the other hand, we can be sure of one thing. If a set delta of clauses is unsatisfiable, then there's guaranteed to be a resolution derivation of the empty clause from delta. And more generally, if a set delta of propositional logic sentences is unsatisfiable, then there's guaranteed to be a resolution derivation of the empty clause from the clausal form of delta. As an example, consider the clauses P or Q, P or not Q, not P or Q, and not P or not Q. There's no truth assignment that satisfies all 4 of these clauses. Consequently, starting with these clauses, we should be able to derive the empty clause. And we can. The resolution derivation is shown here. We resolve the clauses on lines 1 and 2 to produce P, and we resolve the clauses on lines 3 and 4 to produce not P. We then resolve these 2 results with each other to derive the empty clause. The good news is that we can use this fact to produce a method for determining logical entailment as well. Recall that the satisfiability theorem, or maybe it was called the unsatisfiability theorem, introduced earlier in the course, tells us that a set delta of sentences logically entails a sentence phi if and only if the set delta union not phi is inconsistent. So, to determine logical entailment, all we need to do is to negate our goal, add it to our premises, and use resolution to determine whether the resulting set is unsatisfiable. Let's capture this idea with some definitions. A resolution proof of a sentence phi from a set delta of sentences is a resolution derivation of the empty clause from the clausal form of delta union not phi. And a sentence phi is provable from a set of sentences delta by propositional resolution, if and only if there's a resolution proof of phi from delta. As an example of a resolution proof, consider one of the problems we saw in Chapter 3. We have the 3 premises shown here. We believe P implies Q, and we believe that P implies Q implies Q implies R. Our goal is to prove that R is true. To this end, we negate our goal and add it to our premises, as shown here on the left, and we convert to clausal form, leading to the clauses shown here on the right. Note that the third premise here leads to 2 clauses, not just 1. And a resolution proof is shown here, resolving the first clause with the second. We get the clause Q, shown on line 6. Resolving this with the fourth clause gives us R, shown on line 7. And resolving this with the clause on line 5 gives us the empty clause, thus proving our result. Here's another example, this time illustrating the way in which we can use resolution to prove valid sentences. Let's say that we have no premises at all, and we want to prove P implies Q implies P, which is an instance of the implication creation axiom schema we saw earlier. The first step is to negate this sentence and convert to clausal form. Here's a trace of the conversion process. We first eliminate the implication operators. We push the negations to the inside over several steps. We distribute. And finally, we convert the clauses, two clauses, ending up with three different clauses, P, Q, and not P. Finally, we take those clauses and produce a resolution derivation of the empty clause. In this case, it takes just one step. This exercise tests your understanding of the resolution method.